Hello. This is a game called Factorio that I've been playing for a few weeks, and it's been a lot of fun. While playing it, I realized that this is a pretty good way of learning about process design, not only from the perspective of getting better at the game, but at applying process design in the real world. So what I've decided to do is create this video, and it's a series of scenarios that illustrate a few of the basic principles of process design and optimization. And just to give you a little overview, so in Factorio you start in this world, and in this world all you have are resources and just yourself, and you can make certain things by yourself, and then over time you just keep adding complexity and complexity and complexity and complexity, and the ultimate goal is to create a rocket and launch a satellite. And at that point you've won the game, although you can keep playing. And what we can see, let me show you. So this section in here is from early in my game, and you can see a lot of different machines here. There are machines that mine different sorts of materials. There are machines that process those materials from raw materials into more refined materials. So you might mine copper, and you process that into copper plate, and then you process that into copper coils for doing electronic stuff. So very typically you need multiple components to make the next component. And a lot of what you do, you can see that's early, and then we get into, bigger sets, and then bigger sets as we go on. And then over here on the left, kind of in the middle, this has to do with petroleum, and that has different processors and different constraints. But a lot of what you have to deal with is just resources. How do I get resources in? How do I make sure I have enough resources to do what I want? How do I optimize for that for specific resources? How do I make sure I'm not starved? And all of those concerns are really the concerns you need to worry about when you're doing process design. So that's the intro. I will now flip into a number of different scenarios. Here's the first scenario. So what I have is I have here a little electric miner that's going to mine some iron ore, send it out, it'll get put into a box, and then pulled out of the box and put in an electric furnace, and then converted to iron plate, and then finally put in this final box. So what initially we're trying to do is figure out where the constraints are, or where the bottlenecks are in this system. And I'm going to start, I can kind of control what are called speed optimizations. So I can kind of control the behavior a little bit. So they're flashing this because they don't have any power, which is deliberate. So I wanted to wait. So now, let's turn it on and watch it. So we can see iron ore come in and gets put here, and then it's put in, and then we can see here, if we look in this box, we can see that iron plate is ending up. So we're sitting and watching this process, and it looks, you first look at the process and it looks like it's just smooth. So how can we determine which of these is the constraint? Is the constraint that the miner isn't fast enough, or is the constraint that the furnace isn't fast enough? And there's a general rule for how you do this, and the general rule says look at the interfaces between them, and very specifically look at the queue between them. Now, the queue is actually the box. So what do we see? Well, we look in the box and we see that there's somewhere around 20, 22, 23 pieces of iron ore in there. So what that means is we are accumulating iron ore in this box. So therefore it means that we're producing iron ore faster than the furnace can grab it. So we actually have a constraint here on the furnace. Now let's turn off the power. I'm gonna empty out the box, and let me change things a little bit. So I've changed things around. Turn the power back on again. And let that run for a while. And once again, if we look at these two individual processes, you look at the miner, I really can't tell, I can tell it's mining. I can't tell, whether that's a meaningful rate or not, and same for the electric furnace. So we let that run for a while, and then we look at the box, and we see, okay, now in this situation, the steel chest doesn't have anything accumulating in it. So because I switched around the speeds, this furnace is no longer a constraint. The furnace is faster, so now our supply here is the constraint. So that's the first little point. If you want to understand where your bottlenecks are, you look for where material lines up. Material might be physical material. It might be, if you're in a software world, it might be work items or bugs or that sort of thing. That is where your constraint is beyond the point where you do that. So that's the first one. I'm going to complicate this a little bit and come back. Here we have another situation. And in this situation, we have on the left here, we have the miner, and in the middle we're making iron plate, and then here we're going to make gears from the iron plate. So we have 3 sections hooked together. Let me go over and we'll turn it on. And we can just sit and watch. So I want to kind of get into a steady state here. I've added the long conveyor belts, partly because that makes the queues visible, and partly because that's a pretty typical state to be in Factorio, or at least when I've been playing. So if we're in this state, what can we tell? So it looks to me, I said, we should look where the queues are. And it's pretty clear that we have a queue in front of the electric furnace. And we don't have any queues elsewhere. We don't have a queue in front of the gear maker, at least as far as we can tell. We don't have a queue there. So where does this suggest our bottleneck is? Our bottleneck or constraint is in the electric furnace. Okay, really not much of a surprise. The interesting point here from a process perspective is if we're trying to improve over here the number of gears that were coming out, the only thing right now that will improve that is working on this bottleneck. We can mine faster, or we can make gears faster, but optimizations there don't help us at all. And this is one of the important points about processes. Optimizing the non-constraints never helps. Now, if you think of these as 3 separate organizations, the way that most businesses look at this is they tend to do local optimization. So you can think we have a group that's in charge of running mining, and they just try to mine as well as they can. We have a group in charge of running the furnaces. They try to do that well. And we have a group in charge of running gears, and they try to make that work really well. But it turns out that 2 of our groups, the miners and the gear makers, are just wasting their time. And what really matters is interface, essentially the interface between the miners and the furnace makers, or to make the furnace makers more effective. So what we need to do from an optimization standpoint is look at the area holistically, or look at the whole organization holistically, rather than looking at these individual functions. Now, in most teams, you would find that going from one team to another is termed a handoff. And generally, there's nobody that owns the handoffs. So they don't get much focus, but in fact, that's the part that's causing us problems. So let's just go. I happen to have another furnace here. So I've added a furnace, give it some power. And I'm going to give both of those furnaces the ability to run faster. So what did we notice? So I affected the constraint, or the bottleneck, and I improved its throughput a lot. And what do we notice about the overall throughput here? Well, we may not have been paying attention to that, but I can tell you that the gears coming out of here are coming out much, much, much faster. Simply because these guys are working much faster. Now I want to sit and watch this for a little, because I'm kind of expecting something will happen. And if we look at this right now, what do we think about our bottlenecks? So I clearly made the spot that was an obvious bottleneck, I made it much faster. So is it still the bottleneck? Well, what did I say earlier? How do you find the bottlenecks? Well, you look for the queues in front of the bottlenecks. And where do we see the queue? Well, even though these guys got faster, we still see this queue of unprocessed ore here. So that means these two, the furnaces are still the bottlenecks, right? Well, actually, that's not really the case. If you look at this queue here, what you'll notice is that it's getting shorter. So what's important is the dynamic state of the queue, not the size of the queue, really. Now, typically, when you have big queues, if you think in the software world, if you have big backlogs, in the physical world, if you have lots of pre-made material, it can actually be very hard to figure out what the change in rate is. So this kind of takes me to another principle, which is big queues are bad. And big queues are bad simply because it's really hard to figure out what the behavior is. We couldn't actually tell immediately where the bottleneck was in this case because we had all of this other stuff. And in fact, this happens pretty often if you play the game. You might have a big long conveyor with a ton of iron ore on it, and you add more processing capability and you think everything's fine. And then you come back 5 or 10 minutes later and guess what? Your processing ability has now eaten up all that queue, and you now have problems. And if you look at these two furnaces, we see this one is the first one, and it's glowing almost all the time. But this one is barely looking, is only on sometimes. It's off right now. Every once in a while, it'll get something to process. When it gets enough, it processes, but then it's off again. So we've added capability here and pushed the constraint or the bottleneck up here. So kind of to summarize, the point is that where the queues are can be misleading. What we care is about the dynamic state. Shorter queues are generally better. It would have been really more obvious, if I just had a queue running from here just across, to these two guys, it would have been much more obvious that the queue was going away. But because we had a long queue, it wasn't very obvious. One way to look at this is the difference of going from 10 to 5 or 10 to 2 is something you generally notice. The difference of going from 500 to 490, you don't notice. You get these big queues. This is really common in software when you get bugs or very large work lists. It's just very hard to figure out what the item is. So that's the second set of principles. Here's a slightly more sophisticated scenario. So here I've added, we now have 2 miners up here. And then we have some really long queues here. So let that go, and now we have and this goes down some depth and then comes back. So you can think of that as meaning that these guys are a long way away. So the 2 furnaces are a long way away from the miners. Might be think of that from an organizational perspective or maybe a physical perspective. And we have a lot of inventory here. So if you're in the software world, think of that as, hey, we have a lot of user stories or a lot of bugs or something else. So this is kind of the steady state, and hey, it looks okay. We're getting through. What's getting here is something these furnaces can handle. So what I'm going to do is I'm going to go and mess things up a little. So generally, these guys are going to produce iron ore, and that's what everyone wants. So they're producing high quality product. The product is exactly what they need. But what if they start having some quality issues? And I'm going to simulate this here by setting it up so that we end up with some stone into the system. Actually, quite a bit of stone. And you can think of that as flawed product, or you can think of that as bugs, or just things that aren't done correctly. In the software world, maybe these are bug reports, but they aren't very good, or they're old, or something like that. So let's keep watching and see what comes out of this system. And I hope I put in enough stone to cause the problem. So we're going along and we're processing fine. I chose this scenario because this is another one that happens actually pretty often in Factorio. And it turns out that these electric furnaces are not very discerning. If we give them bad quality assemblies, they just do what they think they can with that. I don't know if you notice over here, sometimes they're processing iron. Sometimes they're processing and sending out these bricks. And guess what? These bricks are stone bricks. And the bad quality stuff is now filtering through later in the process. And what's happened? Well, we've gone to a point, I don't know if this is test or somewhere later in the issue, somewhere later in the process. And these substandard assemblies, indicated by bricks, just don't work. But the problem we had was we were generating these, but it took a long time for them to make through here in the process. And because it took a long time, we ended up in this state where we were generating bad stuff for a long time, but we really didn't know about it. If you're in the software world and you've ever looked at bug backlogs, what you find is, bugs that are more than six weeks, or especially 6 months old, you actually don't know if they're bugs anymore. So they're low quality, and if you start feeding them into the system and try to fix them, you can waste a lot of time. So this is another case where big queues are just a really problematic issue. If we had an arrangement, and I'll just draw it in here, since I can. If we had an arrangement that looked like this, notice how much shorter, I'll cut this one off. Notice how much shorter our queue is now. You know, we don't have more than, what would I say, 10 or 12 items in this queue now. So if we started throwing the wrong sort of thing into this queue, we'd find out really, really quickly. So these long queues are just generally a bad idea. If it turns out that you can generate a lot here, you should either work to get rid of this bottleneck or figure out a way just not to accumulate the queue. So that's the end of this one. Here's one more scenario I'd like to talk about. Let's start by turning on some power. So this is a more complex thing. What we're doing is we're making these little electronic circuits. So that we need iron, that goes through the furnace to make iron plates. Then we have copper, that goes through the furnace to make copper plates, and then goes into this assembler, and this assembler makes copper cable. And then finally down here, plates plus copper cable gives us the electronic circuits. So what we can see is, I forgot one here. What we can see is we have this nice product going on. It looks like it's going pretty steadily. You can think of these as maybe different teams again, different teams doing different processes. And so then something happens. And what happens is one of the managers comes up and says, yeah, you guys here in this final assembly thing, we need you to make us some pumps. So you need to switch over and start making pumps. It's like, okay, pumps take different materials. They take steel, an engine plate, and pipe. So let's give that to him. There's the pipe. There's the steel. There's some engine units. And now we can go off. And this guy is now making these pumps. And everyone else is still doing their normal work. So everything is just fine. We've come in, we've kind of interrupted these people, but everyone else doesn't have any trouble at all. This is often known as kind of an interrupt, or sometimes it's known as expediting. And expediting looks like it's okay. But what we're missing is we're building up queues. So if we look here, look in this steel chest. Before we didn't have any copper here. Now we have like 70 units of copper here. We look here, we have like 56 units of steel plate. Now what that means is either, you know, we're getting behind, we're not going to be able to produce those electronic circuits, or we're going to run into some other trouble. So turn that off so we don't use all those up. So the problem we've had is we're really messing up this whole overall system. And we're going to cause problems, but it's hidden because we have these queues. So I'm going to turn off the power. And let's do some modifications here. Instead of having these queues, I'm just going to put, I can probably get away without the conveyor belts, but I'm going to put single conveyor belts here. Because I think that'll be a little more obvious what's going on. Okay, so let's switch back. So this guy is back to the world where he's making circuits. So that's great. And I'll set up that guy for when we need him later. Okay, so he's back to where we can make circuits. Let's turn on the power again, get back to our steady state. That's a little nicer just to look at. We can see the copper plates actually get handed off here. We can see the steel plates get handed off. So everything is just fine. It looks like exactly what we had before. Now we can see, if we look down here, sometimes we get some steel accumulating. So we can see there, maybe there's a little queue here. So that might help us identify the bottleneck. Where before, okay, we could have looked in the chest. So that would have been okay. But once again, we get that same request. You guys need to go make some pumps. So let's flip over. And let's make some pumps. And now look what happened to the rest of the system. We're here making pumps. What is everyone else doing? Well, they can't do anything. And the reason they can't do anything is because we are enforcing small queues. And we're enforcing small queues because we don't want to accumulate a lot of intermediate inventory. Because we know from the earlier steps that intermediate inventory is bad. So if we have a system like this, where we have small queues, then the impact of trying to expedite and ask people to do specific work becomes much more apparent in the system. Now, maybe there are times you really need to expedite. You really need to build those pumps. Or you have bugs that you really need the team to fix. It's just absolutely critical that they fix them. But the rest of the time, you should know what the impact of the expediting is on your overall process. And here it's really obvious. You know, if you're going to make the switch to expediting, that means we're going to make everyone stop, and everyone's going to work on this. So the true impact of expediting shows up when you have small queues. When you have big queues, it doesn't show up. And that means that expediting is much more likely to happen much more often. So this is another reason I really like small queues. Here's another scenario. So we are going to start creating a new product. And in the real world, you can think of this as just some sort of product. In the software world, maybe it's a new program. From a Factorio perspective, we're creating red science automation packs. And these are going to be used to do research. And to build them, we need copper plate, and then we need iron gears. And we've already built up here in the top a nice little section to minus some copper and create copper plate. So that's set. And off on the right here, we have space to expand if we're going to need more copper plate. So first thing we're going to do is add in a section. I'm using the bots to do this, and this is adding in a section to actually create the little red automation pieces. So we have our copper here. So now if I go into one of these, you can see it takes copper plate, and we have that, but we don't have any iron gear wheels. So I need to figure out how to get those. And nicely below us, we have this whole big section here that's set up for iron mining. So it creates iron and a bunch of furnaces create iron plate, and then it feeds down here to create different products. So iron chests, pipe, iron rods, and then gears. So this is great. We have some gears. So this would be really nice. It looks like we already have a group that is producing what we need, or a group that is tasked to do what we need. So we go and talk with that group and say, can you give us some gears? And they say, well, you know, we have a bunch of, already commitments. You can see we ship off some things down below to other users. But sure, we can give you some gears. So let's go ahead and turn that on. And I'll go up here. We need to feed right into here. So, and we'll wait, and we can see down here lots of stuff is happening. Iron's going through, the furnaces are running. they're creating a lot of plate, that's going in, and gears are coming out. And we can see, well, because there are a lot of users for gears, and this group already has essentially contracts, agreements with those other plates, other companies, or other parts of the company, we can see that we're not getting a lot of gears. So we see gear come here, gear come here, gear come here. So we sit and wait. And this is one of the problems with going to another group. It's like we ask them to do something, they have specific schedules, and they have existing commitments already. So we can only get their help to the extent that they're able to give it based upon their other commitments. So finally, I've seen a gear came in here. We're now building an automation guy. And then come through, we get another, and we're building another automation guy. 1001, 1002, 1000. So we're building like one every 10 seconds. And you can see not only we're not utilizing this assembler very well, nor are we utilizing any of the others. And the basic problem is, well, this team down here has their own charter. And their charter is building a whole bunch of different things for different teams. And that's kind of what their goal is. And we might have some influence over them, but in general, we're not going to have enough influence for them to totally change what they do. And in fact, we can go back and talk with them and say, well, we want some more gears. What can you give us? And they kind of say, well, I mean, look at our setup here. It's like, you know, we're already creating almost all the plate we can, and you know, we're running out, we're using all of it. So maybe we could add one gear thing, but you know, at best we can maybe just double, you know, the number of gears you're getting. And it's just not very much. And this is kind of a basic principle, both in process design and in Agile, if we're looking at it from the software perspective. And the basic principle says that, you know, our ability to be effective depends entirely on our ability to control our own destiny. And here, this shows, you know, we have this team centralized around doing iron, and that looks, you know, on its surface like a really good thing. It's like everyone knows how to build these iron plates and build these other things. But it turns out that we're paying for something. We're centralizing here, but we're losing all the flexibility that we might have elsewhere. So what would we like to do? Well, we'd like to do something like this. And we'll see if this works. Once again, the bots come out. And I have to add in one little extra thing. And what did I add there? Well, I essentially added our own gear creating automation. So what you'll see, it'll take this as a little bit of time to get started. But what you'll see is our group now controls our own destiny. We can go all the way from iron ore all the way to the red science packs. And if you look at the number of gears coming off here, wow, that's a whole lot more, you know. Instead of one every 10 seconds, you know, we have quite a few going through here, and we can actually see all 4 of our assemblers are now working, and look at all of these automation packs that are come off. So it's always very tempting to look at centralization as a way to get efficiency. But you have to remember that efficiency in one thing may not translate to effectiveness somewhere else. This whole section down here is very efficient, but it didn't help us at all, just because it's a separate group, and because they're centralized, they have their own charter. So in the software world, this is why it's really useful to have teams that are full stack. So if you have a full stack team, they can do everything from mining their iron ore to creating their iron plate to creating their gears to mining copper ore and to creating copper plate. They simply have the ability to do all of that. And most importantly, they have the ability to look at the entire process and figure out what's going well and what's going slow. So we can look at this, and now they have control on themselves. And if they want to go faster, can we find a bottleneck? Well, it's actually pretty obvious. If we look here, we see a bunch of gears lining up, and we see a whole bunch of copper plate. So we have a lot more capacity for copper plate than we need. And we have more capacity for gears than we need right now. So what that means is we could use our space over here to add more assemblers. Or find a way to run the assemblers faster. Maybe that's another option. So, that's all I wanted to show in this scenario. Think about centralization. Sometimes is a good thing, but a lot of times centralization is a bad thing if you're concerned about efficiency. And seriously, not only is Factorio really useful to learn processes stuff, and it's fun doing that side, it also has this other side. Basically, the pollution you create has essentially spawns these creatures. And then you end up having essentially to go out and try to fix that. So I'm driving around in a tank here. You notice the kind of dome-looking things. The dome-looking things are where they spawn out of. And since I'm late in the game and have done enough research, I can use artillery. If you look in the upper right, run away! If you look in the upper right, you'll see shells coming in while I try to run away from these guys. And here, this is a giant. I might end up dying from this group. So anyway, great game. Just a whole lot of fun. And as I said, teaches you a lot about processes if you look at it from that perspective. So I'm just going to drive around and see how bad of a mess I can get into. In this setup, the artillery essentially has a short range normally, but if you go out and control it, you can get a longer range. So I'm using this little remote here. And of course, to make this work, you had to spend a lot of time coming up with the infrastructure to build the artillery and to create the artillery shells and everything else you need. So it's just me driving around. So anyway, I hope that was useful. I think the process perspective is really kind of an interesting one, and I really like that I was able to approach things pretty simply. I'll put a few links of resources you might want to check out at the end of this that maybe talk about this a little bit more. So thanks for your attention.